All right. Then thank you again for inviting me to the second edition of the summer school. It's a great pleasure to be here. And after this excellent talk of Xavi with these introductory concepts on the deep learning, what I'm going to talk is about some of the works that we've been doing in our group. My name is Francesc Moreno. I'm a researcher in the Institute of Robotics. So I'm going to talk about some of the work, and you'll see some of the applications that we've been doing in the last few years on the topic of modeling humans and their contextual interactions. I'm going to talk about different topics, more or less all of them related. But after every topic, if you want, you can ask me anything, all right? So basically what we want to do in our group is given, for instance, one single image of a person, we want to recover different aspects of this person, all right? Like, for instance, here, what we want to do is from this single image to recover the pose of the skeleton, all right? The 3D position of every joint of the person. That's one of the works I will talk about. Then I'll talk also about 3D closed reconstruction, all right? Given one single image of a deformable object. So we want to retrieve the 3D mesh which represents this object. Then I'll talk also about the work in which we simultaneously estimate both the shape of the body and the shape of the clothes, all right? And after this, so these are basically methods that allow you to do a reconstruction, to do regression, but I'll talk also about a little bit about generative models, just a glimpse of some of the works. Later, Alberto Pumarola, he has a specific session on generative models, and he will probably talk in detail about these works. So here, I'll start with this clothes generation. So a method that allows you to generate different types of clothes, just changing some parameters. We can change the geometry of the clothes, all right? So here, a method for generating new images of a person. Let's say that we have a person from one specific viewpoint, and we designed the method to recover the position of the image of this person as it would be seen from a different viewpoint. Here, a work on face animation. Again, from one single image, we were able to generate animations of this person. And in all these works, we didn't take into account the context of the person, but of course, concepts like motion are very related to the context. So if you want to move in an environment, so you need to know what's happening around you. So, and that's what I'm going to try to explain in the last couple of works. One, explain the influence of the context in these methods, right? And one of the methods is motion prediction, so how the context influences the motion prediction. And finally, a work on grasp affordance. So what we do here in this work is, given one single image where it shows several objects, we will design a network that provides the potential hands, configurations of the human hands that can grasp each one of the objects. All right. Okay. So to solve all these problems, we will use deep learning. We could use other methods, but we use deep learning, and we could follow a brute force solution. What does this mean? So it means that we could take our favorite big network, we could set up the hyperparameters of the network, and then we could train it with as much data as we had. For instance, in this case, so it's the problem of 3D human pose estimation. We would fit it with input images and the training data of the 3D skeletons. We would train the network with this data and wait, and we would cross fingers that everything will work. And if it doesn't, then we would just, let me remove this. Okay, right. All right. So if everything works, that's perfect. But if not, which is in the most cases, we should go back to the step number 2 and change the hyperparameters and fit it with more data, change the training and validation splits, etc. All right. But what is the common denominator of all the works that I'll talk about? The common denominator is that we try to design geometrically aware components or constraints to improve the performance of the deep neural networks. improve the performance means, for instance, training with less data, with less supervision of the data, and achieve the results in a much faster way or in a better way, in a more accurate way. All right. And in particular, we explore two main ideas. We explore kinds of data representations with higher levels of expressivity. We pay a lot of attention of how we do represent the data to train the network. And also, we pay attention on designing deep networks that in some way or another, inherently, they reason about the geometry and appearance of the problem. All right. So what do I mean by this? So let's see one example with this first work, all right, on body pose estimation. So here, the objective was the following. Given a single image, we assume that we knew the 2D joints of the in this image. So it can be computed, for instance, using OpenPose. Our goal is to estimate the 3D joints, the 3D position of all the joints of the person. All right. At this point, what we could do is just to use the regression between the 2D joints here and the 3D joints. But instead, we came up with an idea of representing the 2D joints using Euclidean distance matrices and also the 3D joints. What does this mean? So instead of taking the Cartesian coordinates of the joints, we take the pairwise distance between the joints. In this case, on the left, between the pairwise distance in the image plane, and on the right, in the output, the pairwise distance in the Euclidean domain. And we saw and we observed that using this kind of representation was much more adequate. So for instance, this representation is robust to rotations of the body. So if I rotate my body, the 3D Euclidean distance matrices doesn't change, all right? So the distances between the joints remain the same. So this has some interesting properties. And also, by using this kind of rectangular domain, it's much more convenient to exploit convolutional networks. So we can apply convolutions on top of this domain. So, and actually, we solved this problem with a very simple architecture, which is based on some up convolutions and down convolutions, but very, very small. It had only 0.6 mega per meter. All right. So just let me show some results of what we got here. So what you see here on the left, on the top left is the input image of the person. But interestingly, what we did here was to remove just the right arm of the person. So we assumed that the right arm was not observed. So we can see here that we remove 2 columns and 2 rows of the Euclidean distance matrix, right? So this is the input Euclidean distance matrix that we use to fit the system. And that's the output 3D Euclidean distance matrix. And you see that here we have been able to retrieve the position of the joints in the arm. So this can be also seen very clearly in the representation of the output. So you see that the right arm, which is not seen at all, it's very well recovered, and also the rest of the joints of the person. So this is one of the advantages of the Euclidean distance matrices, that they capture very well the correlation between the joints, all right? And even if we do not observe some of the joints, we can infer its position based on the position of the rest of the joints. So more examples here. That's lead sports dataset, the dataset on people performing all kinds of acrobatics in sports. You'll see that even in crazy positions like those, the method works pretty well. So more examples here. All right. Okay, and that's what I wanted to explain, but we went a step farther on this line. So the methods for 3D body pose estimation, most of them estimated the pose of the person in a reference frame which was centered on the person. We didn't know actually how far was the person from the camera. So in the second iteration of this work, what we did was to compute the absolute 3D body pose estimation. We computed also the position of the person with respect to the camera. And the main idea here was that we took the output of a body-centered network, all right, that provide the solution on the body-centered coordinates, and we added this absolute pose layer. So I'll not go into detail, but basically what we did in this absolute pose layer was to compute the geometric equations that map from this body centric to the absolute coordinates. So here, these equations involve the use of the focal length of the camera, but we integrated it within a layer of a deep network. And it was parameter-free, fully differentiable, and we could train everything all together. And at the end, compute both the position of the person, the pose of the person, and also the relative position with respect to the camera. So some results here. So from this single image, you'll see that we recovered the 3D pose of each person, and the spatial layout, the position of every person in the image is quite well achieved. And also here in the bottom, right? So you see that we have the 3 dancers. We don't know the ground truth here, but more or less you can observe that the results are quite coherent. So the metrics here, I don't know if you can see the numbers, but are in millimeters. So, and more or less they are separated by 1.5 meters, and all the metrics are pretty consistent, and especially a spatial relation between the 3 dancers. All right. Okay, so this was the first work I wanted to talk about. If there are no questions, I'll continue, all right, with the second one. This is on 3D cloth reconstruction. First, let me define clearly what was the goal here. So the goal was the following. We had an input image of a cloth or a deformable object in general. It doesn't necessarily need to be a cloth. And we wanted to train a network that estimates a very accurate 3D mesh of this deformable object. So here we had worked in the past before the deep learning on this kind of topic. And what we tried to do is to design a network that emulated what we did in these previous works. All right, so the idea was to try to emulate these traditional approaches by first representing the surface as a mesh. Second, we registered the mesh in 2D. And third, we lift each one of the vertices of this mesh to 3D using different constraints, like isometry, smoothness, and projection consistency. So we tried to emulate these 3 steps in a network. So this is the network that we designed, and it has 3 branches, and every branch does one of the jobs that I just mentioned. So we have on the top the detection branch, that what it does, we take as input the image of the deformable object, we compute some features, and we extract the position of the vertices of the mesh, right, in 2D, in the image plane domain. All right, and we do this in a coarse-defined manner. Then we have a second branch that takes these vertices and lifts them to 3D, all right? So we add the depth information to each one of the 2D vertices of the mesh. And at the end, we have what we call a shape branch that enforces the 3D and 2D consistency, right? And checks that everything gets correctly reprojected and so on. So here, one of the problems that we had, and also Xavi mentioned, is the data. So data is very important. We didn't have data for training this network, so real data. So what we had to do is to build a synthetic data set. So we built a data set with 120,000 images, with 9 × 9 meshes. We changed the textures. The deformation was simulated by hanging the clothes from a specific point and moving with the wind. And we also changed the illumination, the materials, etc. All right. And with this, we designed several experiments. First, we tested on textures that were already seen at train, so known texture here. We also tested on new textures. We also tested on new textures that were not seen at train, with surfaces which are not textured at all. And we also introduced this kind of synthetic occlusions, all right? And we compared with the traditional methods that didn't use deep learning, right? So, and what we saw is that we were kind of a bit better than these methods. So the improvement in accuracy was not that large, but the important thing is that we could solve the problem with no need to have 2D registration of the points. So these methods needed to know correspondences between the image and a model, which was very hard to obtain. We didn't need that, so we solved it automatically. And of course, after training the network, we could solve the problem in about 100 times faster. And another interesting point is that we also tried what at the beginning I called the brute force solution. Just take a ResNet, feed it with pass the input image through this ResNet, and extract the 3D coordinates without reasoning on the 3 layers that I just mentioned. And using this brute force solution didn't work at all. It only worked for the known textures, but when we tried to generalize to new textures or known textures, it just broke completely. So here, another example of this method on a real experiment, a real data set, right? And again, more or less the same performance. The ResNet, the brute force solution didn't work at all, while our DeformNet, which is this example here on the bottom right, it's the one that worked the best and fastest. Okay, so yes, I think there are a couple of questions here. Yes, so Tian Tan asked if we needed, in the first case of the 3D human pose, if we needed the camera focal length. Yes, we need the camera focal length, but in all these works, we made just a simple approximation of the focal length based on an assumption of the size of the panorama. All right, and I think that it's more or less the same question that Gloria Beraldo asked. Is that the camera angle for 3D close reconstruction? Not really. Not really. No. We didn't pay attention in the case. So Tien Tan is asking, is that the camera angle for 3D close reconstruction important? No. As far as we can see the whole cloth, it's not important. So no, not really. All right. Then let's move on to this third work. Sorry, I don't know if there is a lot of noise. There is noise in the street here. I hope you can hear me well. Can someone confirm?
Yes, we can hear you well. Yeah.
All right. So let's talk about the third work. This is on body and cloth shape reconstruction. So here, the motivation was the following. Modeling the geometry of clothed humans is today still an open problem. So it was an open problem when we did this work in 2019, right? But still today it's not a solved problem. And the problem that is definitely not solved still so far is that there is no large public data set on 3D dressed humans. So if we wanted to train a network for this, we didn't have data. So the objectives of this work were threefold. First, we tried to build a large data set of synthetic dressed humans. Then we proposed also a representation for the 3D shape, which was appropriate for training deep networks. And we designed also a deep network to infer the 3D body and cloth shape from single images. All right. So I'm going to talk one by one of all these contributions. First, the 3D people data set, right? So here, to train our network, we need to create, again, a data set, and we presented the 3D people data set, which is a very large data set with 2 million images, with 80 different subjects performing 70 different actions from different viewpoints, and we also changed it randomly the background, as you can see here. All right, and what we provided in this data set are the 3D models, all right, the skeletons, the normals, the optical flow, the cloth labels, etc., and the body labels. So this could be used for many different problems. So this data set is very rich, but the first problem that we try to tackle is the one on cloth reconstruction. So here I just compared this data set with another data set that existed at the moment, which was the surreal data set. And the main difference is that this data set, probably it's more clear in this next slide, this data set, the surreal, all right, didn't have a 3D geometry for each one of the clothes, and actually only painted the 3D, the clothes on top of a naked body. So the clothes didn't have their own geometry, all right? So now that we have the data set, I'm going to present the problem that we want to solve. Given the input image, we want to train a network that is able to estimate the 3D shape of the person and the clothes, right? But here, again, the first problem that we encounter is what is the best way to represent the shape? Should we use a parametric model, a 3D point cloud, voxels, octree? This is still an open problem, so it's not very clear what is the best way to represent the shape in order to train a network. So what we proposed in this work was to use what is called the geometry image. This is a concept that goes back to a CSIC in 2002, all right, which basically what it tries to do is, given a 3D mesh, it maps this 3D mesh to a 2D domain, right? It does it with several steps. So first, if we take our 3D mesh, we map it to a spherical, to a sphere. This is an optimization process that maps every vertex of this mesh on top of sphere. Then this sphere is mapped onto octahedron, all right? And then now imagine that you cut the octahedron from the back and you unfold it. And if you do this, you can finally transform this initial 3D mesh to a 2D domain. This is the geometry image, which is a 3-dimensional image where every entry here is an X, Y, Z point, which falls on top of this initial geometry here. So once we have this representation of the meshes, the problem is much simpler, okay? So then we only need given input images to train a network that estimates these geometry images. All right, and we can, again, exploit here fully convolutional networks. So here is a glimpse of the network that we use, the GymNet we call, all right? That the idea is that given an input image of the person plus the 2D pose of the person, all right? So we first estimated, we had a multi-scale regressor, so it means that we estimated the geometry image at different scales. And interestingly, we also had what is called a discriminator that checks if the generated geometry image is plausible or not based on different examples that we have, right? And this discriminator work at different scales. We check the consistency at the global scale and at local scale. And I'll jump to the results. So here, given these input images, in this case, these are synthetic images. These are the results that we obtained, all right? And from two different viewpoints. And what I show here is that if we used the ground truth gym, the ground truth geometry image, we would get still a not perfect shape because the geometry image also has some small error, but in any case, we could estimate the 3D geometry quite well. Especially what is very challenging is the recover the geometry of these long dresses from single images. We also tested these on real images. We have some results, and the work kind of performed quite well. All right. So here, what you see is that some of the examples have some spikes, and that's one of the disadvantages of these methods that estimate the 3D position of every point of the GymNet. So the gym is a geometry image which is a 120 times 120, so that's a lot of points. And even if only one of these points is not correctly estimated, it produces this kind of weird artifacts. But this could be removed in post-processing. All right, so no questions here. All right, then let's continue. So what I've presented is so far is 3 different works on regressive models. All right, they estimate the geometry of the body and the cloth shape, and they are fully supervised. So I'll continue the presentation with 3 more works, but in this case, these 3 works are generative models. Generative models means that instead of trying to recover the geometry in the first case or the appearance, what we try to do is to generate new things. In the first work, we try to generate new clothes, and here in these other 2 works, we generate new images of the person or the face. All right. And importantly is that 2 of these works are weakly supervised. Xavi already introduced the concept of the level of supervision, and here I'll explain 2 cases of using quickly supervised data. All right, let's start with the cloth generation work. This is a work that we presented last week at the CVPR, so it's very recent. And here the idea is the following. So we want to generate the geometry of clothes, right? So we want to train a network, in this case, for instance, a t-shirt net, that given some input parameters, it provides the geometry of a t-shirt. But what is the limitation of current approaches is that if you want to generate a network that instead of generating, to train a network that instead of generating t-shirts, it generates jackets, so you need to train a different network, all right? So the current approaches need to train a specific model per cloth topology. So the main contribution of the work that we presented, that's called simplicity, is that with a single network, we were able to represent different cloth topologies. So by changing the input parameters of the network, we can smoothly transition between different topologies, different sizes of the length, etc. All right. This was the main contribution of this work. So how did it work? So just going to give some ideas of how we trained this network. So during the training, we assume that we have the data. Again, in this case, it's fully supervised data. So it means that we have a 3D body and the cloth on the top. So, and how do we represent this? Again, it's very important, the representation. So we use what is called the UV map. UV map is you take the cloth, the 3D shape of the person, and you represent it in 2D. Just open each one of the parts of the body, all right? And you represent this in 2D. And then what we did is to represent the occlusion, the area which was occluded by the cloth. So we use this occlusion map on top of the UV body, right? This was the representation of the clothes. We passed this through an image encoder, and then we estimated 2 different latent spaces, 2 small variables, z-cut and z-style, right? That encoded, the cut encodes the area of the body which is occluded by the cloth. So this can encode if you are wearing long or short sleeve, for instance. And the style encoded the variations in geometry for clothes having the same occlusion map, like a hoodie, or a t-shirt. So that's from one side. And from the other side, we had the naked body. We took each one of the points of this body and we passed through a decoder. So in this latent space plus the points, they passed through the decoder, and what they returned this decoder is the unsigned distance field. It means that for every point of the naked body, it returns the unsigned distance with respect to the cloth. All right, and that's the network that we will use then at Inference. Okay, so at Inference, how does it work? So we have the cloth and body parameters. So we can just use a slider to select the kind of cloth that we want to generate, and also a slider that allows you to design the geometry of the body. Then we pass this to this network that we train it, and what we do is we query all the points in a 3D volume, right? So for each point of this 3D volume, we pass this latent space, the position of the point, and for each point of this 3D volume, we compute the unsigned distance with respect to the cloth, right? The cloth defined by these sliders here. And when we have this is called the unsigned distance field. When we have this dense unsigned distance field, we apply an algorithm that's called marching cubes, right? That computes the 3D mesh from this unsigned distance field, all right? And that's basically all. Then we also add another network that allows you to do the reposing. If you change the position of the body, it also adapts the geometry of the clothes based on that. All right. Okay, so that's in a glimpse, in a very high level, what the algorithm does. And here, some of the generation capabilities of simplicity. So in the video on the left, for instance, what we see is the effect of changing the principal components of the latent variable called zcut, right? So you see that by changing these principal components, we achieve longer or shorter sleeves, also stretched clothes, etc. If we interpolate within the whole latent space, we transition between different topologies. You can see here that when it becomes a jacket, so it's open. So this is a change in topology, which was very hard to represent in a single model before, but we could do it. And finally, also we see that we can change the body shape and retain the geometry of the clothes. All right, that's the generation capabilities of the simplistic model. Now, how can we exploit this? So we exploited this for reconstructing the geometry of the body and the clothes of the person from one single image, like the paper I explained it before, right? But here the results are quite better. So how did it work? So given an input image, right? So we first used an off-the-shelf cloth segmentation algorithm to separate the input image between the different parts and clothes, all right? Then we used another off-the-shelf algorithm, the Frank mockup, to compute the geometry of the naked body, all right? And then we passed this naked body to an optimizer that estimated the latent space. So the latent zcut and zeta style that I talked before, right? And so as to maximize the projection of each one of the parts of the clothes on top of the segmentation labels, right? And with this, we retrieved this latent space, and we had already the 3D geometry of the associated to this image. Okay, and at the end, what we have is a 3D layer clothing. So it means that we have the 3D shape, but with a semantic interpretation. So it means that it's separated with different clothes, and we know exactly which part of the mesh belongs to which each specific cloth. So some examples of the results. So here you see the results. So for 3 people, 4 people. So we had a reconstruction for the upper body, for the lower body, for the shoes, and also for the hair. All right. Okay. And one important fact is that since we use this parametric model of Frank mockup, we could achieve also quite robust results to occlusions. Okay, more results. Here with really a lot of people. And another application of this work is that since we, from this single image, we achieve the reconstruction of the clothes, but also the semantic interpretation, we can then perform cloth editing, which, for instance, means in this case, we could switch or change the jacket and put a t-shirt or add sandals or shorts. So we can do this after the reconstruction is done. Or in this case, we add the hoodie or we add the boots, etc. Okay, so once we have this semantic reconstruction of the geometry, the cloth editing can be done quite easily. All right, so that was everything for this work. Let's move on with person image. What is the processing speed? Oh, that's a good question. I would say that after everything is trained, it's a few minutes, but not much. So because it has several algorithms, we do have to retrieve the segmentation. We have to apply the Frank mockup, and then our optimization. It takes like 2-3 minutes per image. All right. Okay, so let's move on. So that's a paper that we presented at CBPR 18 on person image synthesis. Here, the goal was the following: we have an input image, and we want to to generate a new image of that person, of how she, in the case, would be seen from a different viewpoint, all right? So, and that's what we achieve, but we want to do for any different viewpoint. And even, for instance, in this challenging case where how this person would be seen from the back. So the main contribution here is that there were already some work that solved this problem, but in contrast to previous approaches, we didn't use the full supervision. So our input data was not pairs of input images and output images. So we only used the input images, but not the output images, only the output desired poses, all right? So this makes more easy to obtain data. So you don't need to have the same person seen from different viewpoints to build the data set. All right, and to solve this, we use this network. So at first sight, it may look a bit cumbersome, but I'll try to explain it step by step, and you'll see that it makes sense. So first, what we have here is the input image and the desired pose. We have a generator, right? That initially it just renders poor noise. So it does nothing at the very beginning. Then what we do is we add a discriminator that what enforces is to generate realistic images, human-like images, all right? But still, this image doesn't correspond to this person, and it doesn't have still the correct pose, the desired pose. So to enforce the pose, what we have is a pose regressor that estimates the pose of this obtained image here by the generator, and it computes, optimizes the loss based on this pose, all right? And what we have here is already the person with the correct pose, but still, it doesn't have the same identity as the input image, right? If we used full supervision, now, if we had this very same person from this viewpoint, we could compute a loss here, optimize over here, but we don't have, remind that we don't have. So what's the trick here? If we don't have this fully supervised data, what we do is a simple trick that's called the cycle consistency trick, that we apply the same generator to try to recover the input image, right? The input image with the pose of that person here. And that's what we do here. So we apply the same generator, we try to retrieve the input image, and now we can compute a loss here and compare these two images. All right, that's basically the idea of the whole pipeline. I'll jump to some results. On the left column, I show you the input image. On the second column, the 2D estimated pose, our estimation here, and the ground truth. And you see that there are some results, especially this one where the input image is the person seen from the front, and we can achieve some kind of estimation of the person as it would be seen from the back, or also in this case, right? So the results are quite impressive. But using this kind of low supervision also creates some artifacts. Not everything is as nice as it would seem here, and it has, of course, some failure cases that there is still room for improvement. So here in the first case, you see that the input phase was not removed from the generated image, or in this case, it appears here a hand which is not correct, or here the pants, the texture of the pants is mapped to the boots and not to the whole pants here. But still, it was a good application and a good demonstration of how the weak supervision could work. All right. Then I'm going to move to the next work I want to talk about. This is on face animation. This is NICCB 18. All right, and then the goal was the following. The goal was, given an input image, just one single image, we wanted to render new images of that person, but with different expressions. So here it's kind of serious or neutral, and we wanted to create this angry, scared, happy, surprised. So this was already solved in the literature. So there were methods that could handle this discrete number of expressions. the main contribution of our work is that we could change the expression in a continuous manner. So if you pay attention, you'll see that we can transition between the different expressions in a very smooth and realistic manner. All right, I don't know if it's clear, but that was the main contribution of the work. So which are the main ingredients of the Ganimation? Ganimation is the name that we gave to the network that we created. So it has two main ingredients. The first one is the use of what is called the action units, right? Action units, what it does, what they are basically representation of the facial, of different muscles of the facial movement. For instance, you can express represent one specific expression by a vector, and this vector is just a set of n real numbers, where each number represents a degree of activation of a specific action unit. For instance, here, the action unit number 45 on the right represents the degree of opening and closing the eyes. All right, or here, this one, the 25, represents the opening of the mouth, etc. And you can represent the expression by just a single vector here. All right, the second main contribution, that was very important as well, was what we call the self-learned face attention model. And what is the idea here? The idea is, let's say that you have this kind of neutral face, and you want to generate this smiley face. So you'll see that there are a lot of pixels in this output image that are exactly the same as those in the input image. So we don't need to make the network to have to learn the appearance of all the pixels in the image. So it needs to change specific parts of the image. So, and that's what we did. We split our generator into a generator that learned which are the relevant parts of the face where the expression is produced. So this map here, all right? And basically, this output image is a linear combination of the input image with this attention map, and this we call this a delta of the RGB, right? It's just a linear combination of the input image and this map and the delta. All right. How does it look, the animation at test? So we have an input image, a vector that represents the desired expression. We pass it through these two generators, the generator for the mask and the generator for the delta of the intensity, and we create the estimated image. All right, this is for test. And for training, what I forgot to say is that we also wanted to exploit a framework with weak supervision. So we didn't use pairs of input and output images of the same person with different expressions. So we only used images of the person with one expression. All right. That's what we use for training, and that's how the network looks at train. All right, and it's actually the idea. It's very similar to the one I presented before. Here we exploit again the cycle consistency trick. So again, at the very beginning, now instead of one generator, we have two: one for the mask and the other for the delta of the RGB. Right, at the very beginning, we only have noise. Then we generate the photorealism with discriminator from a previous paper that was called PatchGAN. All right. Then we enforce the expression to be the same using a regressor that estimated the expression of this image here and compared to the desired expression. And finally, we enforce the identity using the cycle consistency trick, which is applied twice the generator to recover the input image, right? So it's basically the same as explained before, but with the difference that now we have two generators instead of one. Some results here. So that's we have the input image, the desired expression, which is basically a vector, and that's the generated image, right? But how can we smoothly transition between these two expressions? So by simply computing a a weight between the original expression and the desired expression. So we smoothly linear interpolate between the input expression and this output expression here, and we apply this vector to the generator, all right? And we can smoothly change from the input expression to the output one, all right? So here you see the degree of the alpha parameter that we apply to the original expression and is summed to the desired one. So if we apply these images on a GIF, so you'll see that these are the results. So this is basically the previous slide, but we put the images one on top of the other, and you see that it nicely produces the expression from the input to the desired one in a very smooth and realistic manner. And what was very surprising is that it kind of worked also for faces which are completely non-anthropomorphic, like this one on the right. All right, so we didn't have this kind of data in the training, but it also worked in the test. So more examples here. All right, so this character probably is familiar to a lot of you. And in this example, so that's an image of the Pirates of the Caribbean. So just pay attention to each one of the characters, and you'll see how the expression of the face is quite realistically changed. And what was very interesting here is that when we changed the expression, so the image was really well blended on the original image, and that's also a contribution of using this attention map. Since the attention map didn't change the parts of the image which are not interesting for the expression, we could nicely blend the expressions on the original one. All right, that's all what I want to talk about this paper. If there are no questions, I'll jump to the last two works. All right, these works are on exploiting the context for different applications. The first one is on motion prediction. So this is a CVPR last year. So, and the idea was the following. We wanted to predict the future human 3D poses from previous observations. We had several skeletons from the past, and we wanted to predict how these skeletons would move in the future, all right? So this problem was already tackled in the literature, but our main idea here was that the context has a lot of importance in this prediction. So if, for instance, there is a table, right? So this the motion of this person can be highly constrained by this contextual information, all right? So, and the main contribution of this work was how to introduce this contextual information within the prediction of the network. So for this, we used one kind of network architectures that are called graph convolutional network, right? Basically, the nodes of the graph represent each one of the elements of the scene, in this case, a cup. So here there is a cup, the person, and the table. And at the very beginning, we have connection. So every element influences the motion of every element. But observing the past, we learn which are actually the important connections between the elements, all right? And here you will see that, for instance, some of the links have been removed. And that's what we learn from the past information. We learn which are the actual and important interactions between the objects. And then we exploit this for doing the prediction of the words. So this video here shows the degree of interaction between the different elements of this specific scene, right? You'll see that the degree changes with the motion, right? And that's what we use then to perform the prediction. All right. So once we have learned which are the important interactions, we do the actual prediction. And with this is the architecture. We use a standard recurrent network. So we have here the previous PT0, T0 plus 1, PT minus 1 is the past. and this is the feature, right? And we predict the feature using a standard recurrent network. But with the difference that here we input the information of the graph convolutional networks describing the relations between the elements, all right? So we just concatenate the information of the graph for doing this prediction. And we also add another part that allows you to update these interactions in the feature. So we can predict if in the feature the interactions between the different elements will remain or not. All right, some examples here. So here, just let me freeze to explain you what you are seeing here. So here we compared with a paper that's from Martinez et al., previous paper at the CPR, which doesn't use the contextual information. So in red, our context-aware model, and in blue, the ground truth. And here, the lines on the bottom represent the error, all right, of each one of the methods of ours and Martinez. And you'll see that in all the cases, Martinez tends to stay still. So it's more conservative in the prediction that they do. But when we use, oops, sorry, let's go back. When we use the information of the context, we can actually perform much better predictions of the movement. All right, you see always that the green one, the amount of motion of the green one is the smallest, so it's much more conservative. And that's one of the problems also of the recurrent networks that usually tend to converge to a mean position. All right, that's all from this paper. And let's finally move to the last paper. That's on grasp affordance. That's a paper that we presented at last CDPR, right? And here kind of created or invented a new problem, right? And this problem was not formulated in the literature before. And the problem was the following. Given an image with one or several objects, what we wanted to do is to predict how a human would grasp these objects, all right? And as a side results, we also had the reconstruction of the scene. So this has different applications in prosthetic design, human-robot interaction, or VR and AR applications. So there was a kind of similar approach in robotics. So in robotics, given an image of a single object, how a robot would grasp this object. This was already tackled in robotics, but the problem is that usually the manipulators and the grippers of the robots have much a smaller amount of degrees of freedom. So here, to represent this hand, we used a model with 51 degrees of freedom. So the problem was much more challenging here. So first, we had to create a data set. So there was no data set. So as I said, the data sets are very important. So we had to create one. So what we did, we took some 3D models of objects, all right, and we annotated them with different kind of grasp. So here you see on the bottom, so this is the name of the grasp. So we annotated with a taxonomy of 33 different grasps, all right, and we annotated these objects one by one, all right. So this is, for instance, a precision grasp. This grasp is called power grasp. This is a power grasp with the index extended. And then once we annotated these objects, we transferred automatically to real videos, right? So we placed the hands to each one of the videos, each one of the objects for each one of the frames of the videos. And at the end, we end up with 133,000 images of 21 household objects and with 28 million grasps. So which is more than enough to train a network, of course. All right. So this is for generating the data. And as I said, it's very important. And Xavi also mentioned that sometimes you spend more time in generating the data than rather the training the network. But then we solved the problem with, we trained this network that's called the GAN-HAN, all right? So given an input image, we want to estimate the grasp, but we split the network, the task of the network in different jobs. First, we estimate the position or the 3D pose of the object, or we reconstruct the 3D object. So we do the reconstruction of the scene. Then, given this input image and the representation of the scene, what we do is we split the task of predicting the hand in two. First, a classification task that tells you from this taxonomy of 33 grasp, which is the best grasp that could be used to grasp this object, all right? So we first solve a classification problem, and then we already have an initialization for estimating the actual grasp. And that's what we do with the second stage, the grasp refinement. All right, here, I just explained the different losses. I'll not go into detail to this because I'm running out of time, but basically the idea is that here, one of the important ones is the adversarial loss, right? So this, we use the GAN loss, which favors physically implausible hand configurations. And as you'll see in the next slide, if we do not use this adversarial loss, we would have this kind of non-anthropomorphic and weird hands. But by using this loss, which basically tells you how similar the obtained hand is to real hands, we can improve much a lot the estimation of the hand configuration. Some results. So on synthetic data, first what I'll show you is the initial estimate before doing the refinement, and then the results after doing the optimization. And you'll see that after doing the optimization, the grasp is highly refined. And in some of the cases, not this one, here you'll see at the very beginning we have interpretation of the hand within the object. But one of the losses that we try to optimize is to minimize this interpretation, and we optimize this after the optimization. All right. So these are results on synthetic data. And just to finish, it's a different video, yes. In this video, results on real images. This should be a video as well, yes. All right. So you can see that kind of the graphs were quite realistic. All right. So it's time just to conclude. So what where I've presented are different strategies for improving the performance of deep networks. One of the strategies, it's simple in formulation, but not in doing it in practice, is to create the data sets. This can take a lot of time. So for instance, in this 3D people data set, we spent like 6 months, right? And that was the job of 3 people, right? That's very time consuming, but it's a task that sometimes needs to be done. Then importantly, before solving the problem, you have to think a little bit of how you will represent the data. The representation is just paramount. So here we have seen different kind of representations: Euclidean distance matrices, geometry images, unsigned distant fields, action units, or contextual relations with graph convolutional networks. And with this, I've presented different networks for solving the different problems. Some of them were regressive models that could be trained in a supervised manner, generative models that some of them could be trained in a weakly supervised manner. That's important. If you don't have a lot of training data, sometimes you can exploit this weakly supervision. And also one important concept is that some of the tasks, in some of the tasks, you have to exploit the contextual information. And I showed you two specific examples of how this context can be exploited. And last but not least, great thanks to all the co-authors, especially here, Alberto Marola and Enrique Corona, PhD students, who did 99% of the work that I've presented today. So that's all. Thank you.
Thank you very much, Francesc. I think we have several questions here from Tien, Baivia.
All right. Let me see which was the last one.
Human decides.
Human decides the type of grasp depending on the objective. Maybe something to combine the two last words you just presented. I didn't really get human decides the type of grasp depending. Maybe Tien, if you can turn on the mic and explain it.
Yeah, hi, can you hear me?
Yes, perfect.
Yes, so it's like depend if I want to drink the coffee, I will grab it in the how say the grabbing area. If I want to put it somewhere, so I grab it the whole cup of coffee. So it's that is the idea, but just the
yes, definitely. No, that's a very good idea. Yes. This could be also used in the optimization. It's just a matter of adding a different loss based on the intention of the user. That's a very good question. Yes, and
yeah, that's a very nice work. Yeah,
and can be applied. Sure, for sure. Thank you. Then we have another questions. Baiva Harjai asks, are these results transferable to hands with different number of fingers? Yes, actually, we have presented another paper. I didn't present it here, but later we have used the gun hand strategy to train a robotic gripper with multi-fingers. So, of course, you need to change the parametric model to represent the hand, but the idea remains the same. And that's the paper we presented in last ICRA. So, yes, they are transferable. Another question from Cedric. What were the training times, number of GPUs for each the projects you presented? Did some programs require more computing resources than others? So we had different numbers on different projects. For instance, the first one on human pose estimation. So we used since the input data were these Euclidean distance matrices, which were very, very small. The size of these matrices were the size of number of joints, which is around 20. So this could be solved with one single GPU and trained in a few hours. But other works, like the work of the gun hand, this required a whole cluster of GPUs. And actually, we did this during an internship of the Enrique at Neighbor Labs, a company, and in this company we could exploit all the resources that they have. Okay, so there are works for everything. For another question, for the human motion prediction, can it be done in real time? Once the network is trained, everything can can work in real time. Definitely, yes. The training is usually the thing that's slow. But once you have solved this training, then the inference is real time or quasi real time. How difficult was to train this network from scratch without pre-trained models? Daniel Gordo. Daniel Gordo, I don't know which network are you referring? But, well, if you are referring to the gun hand, I can say that it was quite difficult. It took several combinations of the losses before getting some reasonable results. So it's not straightforward at all. So I didn't go into detail with the losses, but we combined like 6-7 different losses. And there are a lot of hyperparameters that you need to tune the importance of every loss. At the end, we end up with some nice combination, but it's not easy at all. But for instance, if we go back to the initial papers, the one on human pose estimation, this was quite easy. So the main contribution on this initial paper was the use of Euclidean distance matrices that allowed easy training. Will you share? Yes, I will share the slides, sure. And all the papers are in my webpage. And I think that's all.
I think so.
Yes. Oh, there is a last one into, did you look into a student-teacher networks instead of GANs to train the hands? No, we didn't. But I don't know what would be the student teacher could be used then afterwards to simplify the network once you have trained it, when you have achieved a good training with a more complex one with the teacher. But we didn't do that. And that's all. Thank you.